Hi guys, Godwin here. This is probably something you guys wouldn't expect to come out, but kanina kasi a question was asked in my friend group. This question exactly. It just piqued my curiosity kasi this is a heat transfer question that had some potential for discussion. I'll read it now. A very long 9 millimeter rod with a thermal conductivity of 178 watts per meter Kelvin is attached to a surface maintained at 258.3 degrees Celsius. The rod is exposed to an environment at a temperature of 26.5 degrees Celsius with a convection heat transfer coefficient of 29 watts per meter squared Kelvin. Now what's asked for is the temperature at the distance of 13 millimeters from the base of the rod in degrees Celsius. So, sabi ko, why a very long rod? And I immediately remembered like rods could become fins, and this is actually a fin design problem. So since wasn't really that good at heat transfer and fin design in general, kasi the teaching was very rushed, I decided to try this problem out. And sabi ko, my intuition here was that if the fin length wasn't given, it's not that important. So let's try this out. I'll just put down the figure's already here pala. I'll just put down the formula, the only formula that we'll need here actually. It's that although it's very packed, so it's that theta is equal to the hyperbolic cosine of ml 1 minus epsilon over hyperbolic cosine of ml. Pwede palang tanggalin yung parenthesis here. So, this is the only equation that I think I need to solve all of this. And so, I branded this as Mehetra meets CALENG1 because there's gonna be an interesting problem later while we're doing this. So, before we start, for all the people who clicked here because they saw CALENG1, and they're probably starting CALENG1 soon or have already finished with CALENG1 and would just like to get a review, I'd just like to introduce you guys to this equation because it looks very complicated, but the formula entails itong theta natin is just the ratio. Okay, it's just the ratio of the temperature at some point in the fin minus the outside temperature, the ambient temperature, which we call as T infinity, over the base, what do you call it? It's the base temperature of the fin, what we call as TO, minus that ambient temperature. So, like how hot or how cold it is, depending on the base temperature of the fin and then the ambient temperature. So that's theta. What we need here is the just the T, right? And so sabi ko nga wala yung wala yung L because it's assumed that it's a very long rod. Okay. Oh, yeah. It's a very long rod. So we'll do some cool stuff with that later. Pero one thing we need to be introduced pa is the ML actually, the whole of ML. So the whole of ML is just square root of, it's not really something you put with just HP over KA. It's actually H bar. Okay, H bar P over KA and then L squared. So you can actually just bring out the L. And so makukuha mo is only M is equal to H bar P over KA. So H bar, that's the convection heat transfer coefficient, also known as the film coefficient. And then the K is the thermal conductivity of the fin. And so yung P and A, P is the perimeter of the shape of the fin, which is a circle. And then A is the area of that surface of the circle. So alam natin, we were given a diameter here, which is 9 millimeters. So maybe we can work in terms of that. We can simplify this further. We can have H bar. So we know that the perimeter of a circle in terms of its diameter is just It's just pi d. And then the area of a circle is just pi over 4d squared. So we can cancel out the pi d, and we are left with, I guess we can put the 4 sa taas din, right? So 4 h bar over k d. Right, wait. Yeah, yeah, that looks fine. Yeah, that looks fine. Okay. So, yeah, that's how we work with the m here. So we can already compute for the m, which I think is, oh, spoilers. That is, sabi ni Desmos, it's 8.509. Okay, let's just write that down. M equals 8.509. Lightly. Okay. And now this naman, this quantity, this epsilon, so epsilon is just the ratio, ano tawag dito? The ratio of what you're looking at, the slice that you're looking at, the x, that distance from that to the total distance of the fin. So that's just x over L. And so wala tayong fin length because it's assumed it's just very long. So this falls apart really easily. So what we can do is okay, we're going to the solution now. We can use that, we can substitute that into the original formula, which gives us theta is equal to cosine, cosine of ml, and then I know that that's x over L over cosine of ml. Okay, and then we distribute the L, and then we're gonna get cosine of m, and then L times 1 is L, L times x minus, L times x over L is just x. And so we get this simpler equation. And so, ito na. What do we do when we're presented with a problem that says just a very long rod? Of course, we're going to have to approximate. We're going to have to measure what this value approaches as L approaches infinity. So, this is where the CALENG1 comes in. Let's find out what theta is by doing the limit of the limit of, ito pala muna, the limit of hyperbolic cosine of m times L minus x over hyperbolic cosine of ml as L approaches infinity. So I said I didn't have time to like write this down and then compute it. I just left it to Desmos, and then sabi ko, I'll just look at like somewhere really far from here. And we have to note that this x-axis actually measures in meters. Kasi I did plug in here. D and E. E yung, for now, that's my x because Desmos is finicky with variables like x. I can't just freely use that. Anyway, so like somewhere in the 40-meter, imagine like a 40-meter long fin. The value of our theta here approaches 0.895. So I was like, okay, just write that down, 0.895, and then use that. And use that to this anong tawag dito? This theta formula and get t, and then done. I was like, okay. But for this video, I just like to solve this with you guys. If you guys want to try this on your own first, sige lang. Go, just pause the video, and when you're done, come back here. Let's see if your solution is faster than I did, because I think my solution is really slow. But for first timers or like ano tawag dito, people who haven't touched limits, especially ones with hyperbolic functions, it's just really the beginner's approach. So let's remember first what cosine is, what the hyperbolic cosine function is actually. So we know that a hyperbolic cosine of something, let's just say A, is just e to the A plus, that's what sets hyperbolic cosine apart from hyperbolic sign. Ang hyperbolic sign kasi is e to the a minus. So either way, e to the a plus e to the negative a over 2. And so we can apply that, what do you call this? We can apply that here. So we're gonna go the limit of, as L approaches infinity here, the limit of, itong dalawa, if we make it in terms of this definition, we know that the denominator of 2 will cancel out because they both have a denominator of 2. The numerator side goes down, the denominator side goes up, and they cancel, and then blah, blah, blah. So we're left with only e to the m times L minus x plus e to the negative m times L minus x over, okay, close enough, e to the ml plus e to the negative ml. And so, what are we going to do with this? Because what's really confusing with this is that we're using x as a constant and not a variable. We're using the L as the variable. So, ayun. If we try to, what do you call this? If we try to substitute directly right now, we'll have infinity minus x. Since x is just a number here, walang kwenta yon, it becomes e to the infinity, which is infinity. And on this side, we have e to the negative infinity, which is 0. Infinity plus 0, that's infinity. And then I don't think I'm breaking any rules there. This is also infinity. This is plus 0, so it's infinity over infinity. So you can do L'Hopital's rule, right? But if you do that, speed differentiation lang tayo dito. I actually want to, what do you call this, expand this for a bit first, especially the numerator side. We'll have e to the ml minus mx plus e to the negative ml plus mx over same thing downstairs. Okay, so if you do L'Hopital's rule here, we remember that it's in terms of L. So what we're deriving is in terms of L. We're going to have the limit of Sir King. Sir King uses that, right? Anyway, we'll have same limit. We're going to derive this. We're going to have, since yung L lang, yung tinatreat natin as variable, so we're only going to bring down the m. So you're going to have m e to the ml minus mx, since mx is just a constant, plus, not plus, sorry, minus, kasi this is minus now, me ml, minus ml plus mx, okay? And then me ml minus me minus ml. Okay. And so, makikita nyo na it's just going to cancel out m. We're going to be left with infinity minus 0 over infinity minus 0. And if you derive again using L'Hopital's rule, it's going to go back to this one. And then, you'll have a dead end. So I do not like that method. I tried that first. I was disappointed. Okay, so we need another, what do you call this? Another way for us to move forward. So I thought this was pretty complicated. So why not make it even more complicated? Just kidding. Okay, let's expand this more using laws of exponents. We'll have limit as L approaches infinity of, since they're just, they're just added together, the exponents, you can do e to the ml times e to the negative mx plus e to the negative ml times e to the mx over the same thing downstairs. Okay. And then you see that these two terms and then these two terms, they're the same. So I said, this is kind of, what do you call this? Kind of complicated for some people. I'll just say that we'll let A be e to the negative mx. And then we'll let B be e to the mx. And then I said, well, I used x and y here. I don't think that will hold. Sige, let's go with the y and z, I guess. Sige, y, let's let y be equal to e to the ml, and then z be equal to the e to the minus ml. And so this turns into the limit of, as L approaches 0, this becomes y, this becomes y, this becomes z, this becomes z, this becomes a, this becomes b. So we'll have ay plus bz over y plus z. And so, okay, let's remove the limit first. We'll go into how we can simplify this first. So naisip ko, how would this, how do you explain this? How would this be decomposed? Yeah, how will this be decomposed? Okay, so let's go into a tangent here. No. Okay. If we, hold on. Okay. If we base just on the y term, we can just divide this a divided by 1 will result in a, right? Okay. Will result in a plus something something, right? So let's base our answer on that, and let's make a times y plus z, since that cancels, that would divide perfectly with our denominator, which is y plus z. Kaso we added something to the numerator which wasn't there. So in order to keep the balance, we need to subtract the same thing, right? So plus bz. What did we add? We added the az, right? So we need minus az. So yz. And so we can write this now as a plus, so z times, was I right in doing this? Yeah. Okay, so let's group the z out. We're gonna have z times b minus a over y plus z. So we can make it like this. Limit of a plus z times b minus a over y plus z. So the reason why I just put the a and b as different from y and z is that a and b are constants, right? And then y and z are terms having something to do with yung variable natin, which is L. So if we transform this back, we will have limit as L approaches infinity. What's our A? Our A is e to the negative mx plus, what's z again? E to the negative ml. What's b minus a? So e to the mx minus e to the negative mx over, what's y plus c? That's e to the ml plus e to the negative ml. And then, let's try to plug in again. So ang paplug in lang natin is with this, and with this. We're going to have negative infinity here. So we'll have 0 anong tawag dito? We'll have 0 sa numerator because these are just numbers. And then the only thing we need for this to become a legit limit is that this does not become 0. The denominator does not become 0, right? So I hope it doesn't become 0, but I don't think it will kasi L, if we put a positive L here, this becomes e to the infinity, which is infinity, plus e to the negative infinity, which is 0. So this becomes 0 over infinity, which is a big cancel. And then finally, since wala namang L dito, the limit of a constant is just e to the negative mx. And if you search in Wikipedia, I overlooked this. For the fin page to, like fin extended surface ata yan. There's a condition there with infinite fin length, and this indeed is the answer. And so, okay, I went on a very big tangent there. Let's just put down here that theta is equal to e to the negative mx. And so, we will have t minus t infinity over t0 minus t infinity, which is equal to e to the negative mx. Mamaya ko na ipa-plug in. So we're looking for t. We'll just do t minus t infinity e to the negative mx times t0 minus t infinity. And then we'll have isolated t, which is t equals t infinity plus e to the negative mx times t0 minus t infinity. And so let's just substitute everything. What's our t infinity again? T infinity is 26.5. 26.5 plus e to the negative. Oh, right. I forgot to check if this is correct. So we know that our m already is the 8.509. So negative 8.509 times x. So our x here is in terms of millimeters. We'll change that to meters. That's going to be 0.013. And we will have, right, 0.895. Okay, let's try e to the, ito ba yun? Okay, e to the negative me. That is indeed 0.895. Yeah, okay. So it is correct, 0.895. All right, so let's just put here, yeah, let's just put here yung mismong value na. Oh, right. Okay, I'll just erase. All right, 0.895. And then this is, what's T0? T0 is 258.3 minus 26.5. Let me just enter that in my calcu. That's close enough, right? 26.5 plus 0.895 times 258.3 minus 26.5. That gives me 233.96. 233.96 degrees Celsius. And that's, oh my goodness. Hello, okay. And that gives us the answer for this really confusing problem with a really long fin. So I hope you guys enjoyed that because, I don't know, magiging spontaneous kind of upload siguro tong series. Should I even call it series if it's only gonna be one video? Anyway, whatever. I hope you guys enjoyed that and keep on learning, please. Yes.